All right, guys, this is the ENEL 469 final report. This is Andy, Wayne, Xiang Sun, Nate Immerkar, and Tristan Luo. Part 1A. It's about this circuit here, LC tank circuit. We're calculating the resonance frequency, which is 1 over 2 pi root LC. Get that to be about 500 kilohertz. You can see it graphed right there. At that point, it's going to have the voltage drop be about 1 volt, and that's because the reactance of the L and the C, it counts each other out, and you get a voltage drop from V out to down here, which you can call ground. Next part, we did a parameter sweep of a capacitor, the capacitor, and it affects the resonance frequency. It decreases it depending, like if you go up or go down. It's going to change the resonance frequency. You can see the movement there. Next part, we added a resistor in parallel. Yes, the peak voltage at the resonance decreases. You can see that, and it's kind of a wider shape now. And then if you're doing it in series, you're going to get a similar reaction as well.
For our active filter, so in the first part, we calculated our values for our circuit, and this is our hand calculations. We figured out our IC1, IC2, VCE1, and VCE2 using the circuit, and then we did our small signal analysis and figured out our gain. And then we simulated it, and then we figured out our gain using the oscilloscope and figuring out how to match these values up. And then we also simulated the gain over here, and then also the glitch in the resonant frequency. This is our response, and then this is us adding the amplitude modulated signal, and this is how we simulated it. And then we also calculate the gain of our circuit using our simulation, and then this is us adding that extra circuit to smooth out the signal and make it a sine wave.
This is the baseband amplifier section of our AM radio. Over here is our DC and small signal analysis to determine our calculated values for the circuit. Over here is our DC simulation showing the collector, base, and emitter voltages and current. Over here is our AC simulation of the oscilloscope waveforms, where green is the output and red is the input, showing a gain of 20 as well as a phase shift of 180 because of the common emitter configuration. And over here is an AC sweep of 1 Hz to 100 megahertz. This is the output buffer of our AM radio. So here is our small signal and DC calculations determining our calculated values for our circuit. This is our DC simulation showing the collector voltages and currents. This is our AC oscilloscope waveforms with red as the input, green as the output. And here is our AC sweep from 1 Hz to 100 megahertz.
Going to our last two modules of our baseband amplifier and our output buffer, we get the waveform we see here where the blue is our input and the red is our output. Now the reason for this phase shift is because in the baseband amplifier is a common emitter, and that causes the 180-degree phase shift. In our output buffer, it's 2 common collectors where there is no phase shift, so this waveform does make sense. Finally, when we put everything together from the antenna to the output buffer, this is the final waveform we get, where the green is our AM signal and the red is our demodularized and amplified signal.
So here's our 469 final circuit for the AM radio. Okay, right here we have our antenna and active filter. Over here is the detection circuit. If we go over here, this part is the baseband amplifier. Over here, this middle section is the output buffer, and we have this going into a power amplifier with a gain of 200, which goes to the speaker. So it's the first channel.